In today's lesson, we are going to understand what is meant by a planar graph and be able to use and apply Euler's formula. A graph is planar if it can be drawn in such a way that none of the edges cross over except when they meet at a vertex. So here is an example of a planar graph. Now pause the slide and investigate which of the complete graphs, K1, K2, K3 and so on, can be drawn in the plane. So which of those graphs are planar? So K1 doesn't contain any edges, so by definition that is a planar graph. And similarly K2 only has one edge, so therefore it is planar as well. K3 has three edges and none of them need to cross in order to draw it in the plane. So K3 is a planar graph. K4, it does depend on how you draw K4, but it is possible to draw it so that none of the edges cross over. In this case, the final edge has to go around the outside in order to avoid crossing the ones already drawn. So that shows us that K1, 2, 3 and 4 are all planar graphs. K5, you can start by trying to draw it without crossing any of the edges. And initially this is possible by going around the outside. But as we draw more edges, it becomes apparent that the last pair cannot be joined, last pair of vertices, unless the edges cross over. There is no way of drawing K5 to avoid edges crossing, so therefore K5 is not a planar graph. Now K6 will also be non-planar because contained within K6 are all the vertices and all the edges of K5. So for that reason, any complete graph where n is greater than 4 will always be non-planar because K5 will always be a subgraph of that. Bipartite graphs can also be planar if it's possible to draw them so that the edges do not cross. So here's an example of a planar bipartite graph. Investigate the complete bipartite graphs with different numbers of vertices on each side to decide which of those are planar. So let's start with the graphs KM1. In other words, complete bipartite graphs that have m vertices on one side and one vertex on the other. So here is K41, and you can see that each of the edges from group 1 join with the vertex in group 2, and there's no limit to how many there could be in group 1. So any bipartite graph will be planar if either m or n is 1. So if one of the groups only contains one vertex, it will always be planar, regardless of how many are in the other group. Now let's consider KM2. So for KM2, you can see that extra edges can be joined from each vertex in group 1 to the second vertex in group 2. So in this case, A, B, C, D can all be joined to vertex Y, even though they are already joined to vertex X, just by going around the outside. And you can see that additional vertices could be joined to group 1, and this pattern could still continue in the same way. So this leads us to the conclusion that any bipartite graph KMN will also be planar if either m or n are 2. If we now try to add an extra vertex to each side, for example K33, you'll see that we can start off trying to connect each vertex in the first group to each vertex in the second group. So A has been joined to X and Y, B has been joined to X and Y, C has been joined to X and Y and Z. You can now see that most of the vertices can be connected together. However, the the final edge, there is no way of connecting A with Z without there being some crossing of the edges. In fact, the bipartite graph K33 is non-planar. It's impossible to draw that in such a way that the edges don't cross. And this leads us to the rule that tells us that for a complete bipartite graph, if both of the groups have more than 2 vertices, then that graph will have to be non-planar. So we've previously defined vertices and edges in relation to graphs. So for each of these 4 graphs, we're going to count V, which is the number of vertices, E, which is the number of edges, and we're also going to count F, which is the number of faces or regions that the graph splits the plane into. So for example, this first graph here has 6 vertices, 7 edges, and the number of regions are 1, 2, and then the outside of the graph is 3. So F would be 3. So pause the slide now and write down the values for the other 3 graphs. So graph 2 has 8 vertices, 11 edges, and 5 regions or faces. Graph 3 has 7 vertices and 6 edges, and you will also notice that because it's a tree, it only has 1 region, just the outside of the graph. So F will be 1 in this case. Notice that because it's a tree, the number of edges is 1 less than the number of vertices. This is always the case if a graph is a tree. Finally, graph 4, the number of vertices is 7, the number of edges is 8, and the number of regions or faces is 3. So can you spot a rule that connects these 3 values together in each case? So the rule that connects the number of vertices, edges, and faces or regions in a connected planar graph follows this rule. This can be simplified to V minus E plus F equals 2. This is known as Euler's formula. Euler's formula also applies to convex polyhedra, such as the Platonic solids in the table below. So here, the number of vertices, edges, and faces on the solid follow the same rule, V minus E plus F equals 2. This is a special case of a more general rule for closed surfaces, known as the Euler characteristic. So certain surfaces will have a different value instead of 2 for the value of V minus E plus F. This is in an area of mathematics often studied at university called topology. Now please complete the questions on the worksheet on Euler's formula for planar graphs.